Hey everyone, welcome to another episode of the Common Lisp Study Group. I'm your host, Vedam with Atlanta Functional Programming. Today we're going to finish up our tour of kind of the Metaobject protocol specification itself with fun-callable standard instances and the what they call an update invocation protocol. This is kind of like the final set of things, really, to kind of cover some of the things in the Metaobject protocol related with generic functions, the generic function invocation protocol, as well as some protocols that they've designed for dependency management. As you recall, Common Lisp itself is a kind of an interactive programming language. That's what it's been designed for. You are kind of molding your application as you are developing these things. So one of the use cases that this dependent maintenance protocol kind of came out of is the need of being able to update information that may have been memoized through the initialization process. And in particular, it's kind of used for dealing with situations where you are adding and removing things from either class Metaobjects or generic Metaobjects. But we'll get to that. Couple of announcements. Again, we're going to be starting in a couple of weeks our game programming series by Michael Fiano. Hopefully, during that time, we'll be able to cover some of the things that might be useful for folks who are planning on doing the game jam this year. I'm, of course, also looking at potentially a couple of other talking points related to some stuff that I've been doing with network programming. We might revive a couple of things related to that, but that is kind of in the next kind of month or so. Another thing I wanted to mention is as usual, folks in the Atlanta area, if you guys are willing to give some talks for Atlanta Functional Programming, please contact me or Judd Taylor with your talking points and either post it on the Functional Programming Slack channel that's on Tech 404. And or if you're willing to talk to me, I'm also available on, of course, the CL study group on Mattermost, as well as the Lisp channel on Functional Programming Slack. So let's begin. Last time when we kind of covered this, we've stopped at this protocol dealing with instance structures, where we were accessing slots and using that to inform enforce a particular ordering. So in our last episode, we kind of actually went through something like this, where we had an ordered class. We went ahead, compute the slots, and depending upon the class slot order that you defined in your slot order annotation, slot order metadata that you provided as being part of the using the ordered class meta class. It went ahead and used that in our compute slots method that would actually end up creating sort of like an implicit sort of the ordering on how different slots were actually going to be defined inside the instance structure itself. This in turn allowed us to actually grab slots directly by index on the instance using a method called C2MOP standard instance access. Now, we may end up using some of these in some of the examples later today, but I want to at least give that kind of a review on this. But notice, up until now, we have been kind of focusing ourselves on standard class, standard object, and being able to define classes are ultimately, data classes that you can actually access information from, and being able to modify some sort of state associated with it. But there's an additional set of classes that are there where you can actually uh, treat those class instances both as normal classes with information and metadata associated with them, and has functions. Now, for folks coming from other languages, this is very similar to implementing callables in, I think, Python. It calls it callables. In C++, it's function objects or functors. And don't confuse functors with the functor term that's commonly used to define objects that implement the map function in functional programming languages. But it's kind of the same thing. It's basically just nothing more than a function object that you can then invoke. These are called in common Lisp funcallable standard classes or funcallable instances. Those classes are basically subclass from funcallable standard class or any subclass of funcallable standard class. By doing so, you'll be able to take an instance and actually be able to pass it to funcall and apply. And whenever you use these instances, there is a function that's attached to a particular instance that is returned. So how would this look? Well, one of the examples that are kind of brought up in the book that I thought we would kind of cover here, something pretty simple. Let's say that we want to create structures with some information, kind of like def struct. Well, of course, since the Common Lisp language has def struct, you don't necessarily have to do something like this. But you could certainly do so in some other situations where you'd want to keep track of some metadata. So in this case, let me just get to my example here. Okay. So in this example, what we're going to be doing is we're going to actually create a class, but instead of actually making a subclass of that class, we are essentially using funcallable standard class directly. Now, notice I had to explicitly in line 10 through 13, well, specifically line 13, when I'm defining the class, I had to explicitly define the meta class to be funcallable standard class. Now, one question that might be brought up is well, why do we need to specify this directly instead of implicitly? Well, as you recall, def class by default always uses the standard class or standard object has its meta class behind the scenes, and this is how it hooks up to the rest of the machinery. Funcallable standard class is, of course, at some point hooked up into the machinery, so it already implements some of the stuff that we had to implement for our own meta classes. Mainly, validate superclass is not actually necessarily required here because we're not actually defining a meta object. We're actually using one. But once you've actually specified this this funcallable standard class as being the meta class of your new user-defined class, it becomes pretty easy now to actually make this into a funcallable instance. Mainly, what you would have to do is you would have to define a after method after initialize instance that would then take whatever information that you specified in your user-defined class and use that to create a function, a lambda function, on top of the instance. So that's used with this call to set funcallable instance function. Now, if you look at the signature here, and if I can actually get my little my IDE Spacemax to actually give me the this stuff in my mini buffer. Hold on a second. I may not have actually loaded this into my Lisp REPL. Okay, now this should work. Okay. Funcallable instance set funcallable instance function takes two arguments. One is the funcallable instance itself, which in this case we just called C. And a new value, which is actually an anonymous function. If you're so inclined, you could go and attach a freaking constant into this. It's kind of dumb if you do that, but you know, certainly that a constant is a constant's function, so that's fine. But it does take in a lambda. It requires to be funcallable, and you know, there should be some sort of logic associated with it. Now, if we look at this function here, this anonymous function, this lambda that we created, this really is nothing more than taking the name and fields of the constructor object that we created, and it just generates a new array that's of size of the 1 plus the number of fields. So, like in this case, name and fields are the only two. In this case, if you pass in 0 arguments, it'll just be 1 and so forth. And what it does is I added this for illustrative purposes. It spits out that this is the name of the instance that we're creating. We're adding values to it, and then we, you know, generate this new instance. So, oops, 1 second. I forgot that I did not load up my compile. No, we can actually compile this guy. Okay. So once we compile, once we have this defined, how do we use this? You know, well, this is an example of how this funcallable instance can be used. This is us defining a test struct here. This test struct is now a funcallable instance, which means you can actually go and define another, you know, variable. Let's call it P1 that takes the result of calling funcall on test struct, and this internally behind the scenes will use that lambda that we've defined in the set funcallable instance, and it will create a new instance of P1 with the array results that we defined inside that that lambda function. And as you can see, they setting values to a new position instance. That's basically it executing line 24 when the funcall is created. And now we have our result when we go and do this. You get the first argument being the name of the class name, which we changed here in line 25. And then since I've created this array of being initial element of 5, it goes ahead and, you know, the rest of the elements will stay the same. They haven't been overridden. So what actually happened here? So when we executed the funcall, it looked at these fields. That's 2. Went ahead and incremented it, created the array, initialized it to 5, then overridden the name, and then created the new instance. So this could be any it doesn't necessarily have to be an array or vector or some sort of built-in operation. You could imagine that this can be some sort of custom information that is generated based on what was passed in the fields of this argument. But regardless, the fact that we were able to actually define something that looks like a callable, a fun callable instance, well, a class, we initialized it using initialize instance. This is kind of the approach of actually defining your own fun callable instance and then using that to construct new instances. That's pretty powerful. You could see that this could be used for other cases. For example, using it for uh, um, creating anonymous inner classes that's commonly used in languages like, say, Java, where you're actually and those are actually themselves callables and delegates that you could then invoke on based on the given situation. There's plenty of other ways, things that you would want to that you can use for this. I'll leave it to your imagination, but the actual code of the funcallable and its use is it's pretty simple in this case. But this is all well and good. We have this standard class for creating funcallable instances, and we have the ability to actually leverage them directly. But what does this have to do with some of the other meta objects in the Metaobject protocol? Well, you need to know that there is about set funcallable instance function because it is directly used in our next topic, which is the generic function invocation protocol. At this point, my YouTubers, if you guys are watching, please free to ask questions. We kind of like those who are just joining us. We kind of like answer questions as we go along. So if there's a particular question you'd like us to ask, answer, please let me know, and I will handle it. Let's answer this one question. So what is the generic function invocation protocol? Well, my understanding in the book, and Michael Gargano, I'm hoping you could you would provide some of your own opinions on this. But the way this sounds like is this protocol works is it's just nothing more than creating kind of a lookup table for all the different combinations of different methods. The way it does this is it creates what's called a discriminating function for every time the generic function itself is invoked. The discriminating function is basically the function that takes the full set of arguments that was received by by the invocation, and based on the types that were passed in, it looks up and executes the appropriate methods and returns the appropriate values based on the method combination that you've defined earlier early on when you defined the generic function. So this process is a pretty simple but pretty important thing to know. The first thing it does is when the generic function is invoked, is it calls a function called compute discriminating function. This guy, all this does is it will go in, take in the arguments, take in the restrictions, look up the method combination, and then compute essentially an instance of a discriminating function that is then stored into the generic function, some sort of data structure that the generic function keeps track of, and it's stored by calling set funcallable instance function on that new entry. Now, one thing to note is whenever you've initialized or reinitialized, or even you've added or removed a method from existing set of objects from the generic function, the discriminating function is always recomputed. So if you're constantly in development in your Lisp image and you're adding and removing methods, This guy, every time the generic function is invoked, it will go ahead, recompute the discriminating function, reset it to using set callable instance function, and then from that time forward, that new computed function is what's used. Now, discriminating functions call two additional methods internally, which is compute applicable methods and compute applicable methods using classes. These two functions are used for the type resolution and the generation of the actual function itself. They apply the types to the generic function's arguments, and then the applicable methods that are returned from these functions are combined using a function called compute effective method. We've actually introduced compute effective method in past episodes when we were introducing the Metaobject protocol in general, but this is something just to kind of be aware of, that by the time you get and you are invoking something, the method that you are actually invoking is the effective method, not anything that was computed before. Then, of course, all the method definition body itself is processed by something that we introduced before called make method lambda. The result of this function is processed to create an actual method function instance. Usually in most modern compilers, Lisp and Lisp distros, and I may be overgeneralizing here. There might be some situations where this isn't the case, but most of the time, if you're using SBCL and CCL, I'm almost certain the method lambda that's returned is actually passed in and processed by compile to generate native code before it produces a method function. Now, of course, if there were some arguments that weren't resolved, there might be additional code for checking those arguments at runtime. If you look at the disassembly, in general, if you have all the types, it will try and optimize and create a native function that's pretty high, that's pretty performant. So there's two things that that happen when the generic function is invoked and the arguments are actually received by this method function. The receiving itself is controlled by a call to a method that's in the method protocol called call method. This is just grabbing those arguments, passing it to the function itself, and it then invokes the function using funcall. Now, method functions usually take two arguments, okay? So this is something that needs to be kind of like talked about. So what are method functions? Let me go ahead and put this up here. Method function objects are kind of generalizations of the function instances themselves. They take in two things. One is the list of arguments for a given generic function that the method function is defined on. And they also take in and this is from computing the applicable methods and computing the applicable methods of classes. It creates a list of next methods that can be leveraged. And again, if you're using standard method combination, the ordering of those methods is based on that chaining. If you remember, it's usually all the before methods, then all the primary methods, and then all the after methods. If you're using method combination, standard method combination, if you have any around methods that are defined, usually the primary method is invoked in the around method in the appropriate way. And if you want to look at the specificity of the before and after methods for folks who haven't looked at our Common Lisp object system series, I encourage you guys to look at that because we've actually talked about the standard method combination in that series. I defer to those for more detailed explanations. Once you have this list of next methods and list of arguments, call method is if call method appears in any of the well, call next method is used within any of the code in your before, after, or primary methods. It'll actually call the call method and it and the list of next method that was passed in during generic function invocation. Those are actually leveraged to actually go through the ordering. Are there any questions so far on this? This is pretty straightforward if you think about how the machinery works and you think about how the common Lisp object system works. But I'll give a second for folks to catch up and give me some thoughts. Okay. So the next thing we're going to be talking about is what's called the dependent maintenance protocol. So I want to first talk about maintenance protocol. I wanted to bring up first kind of the use case of this. So if you guys are creating during the development of your applications, and if you're using the Metaobject protocol especially, there might be a situation where you're defining a lot of these meta objects, and you want them to be performant. So the usual approach to actually make things performant is to cache the computed information at the time that the method object is actually either generated or the first time it's used. So for portable programs especially, for portable programs, often this memoization is includes the method object memoization, that is, includes both portable meta objects that were defined, and as well as implementation specific meta objects that may have been defined. Okay. And this is kind of important to note, because if you are using implementation specific meta objects, there is some restrictions that might create undefined results. The specification does not actually go through and define in clear terms what could happen between for portability. But one of the things regarding this memoization that becomes an issue is something that I mentioned earlier, which is if you end up reinitializing or redefining classes, or modifying generic function meta objects by adding and removing new ones that are coming in either during the application runtime itself or during your own development process, some of the classes that are especially dependent upon these meta objects may get violated. Like, they may not end up having all the information and so forth. And they needed to have a way to actually update the memoized information during those changes. Information during changes in development or at runtime for class meta object redefinition or generic function redefinition, for that matter. is generic function. Well, methods added or removed from a generic function. So the maintenance protocol supports this by essentially allowing you to register an object and get notified via event whenever the the classes that you're dependent on get changed or modified. So it provides support in the following ways. It adds for registration uh, a function called add dependent, which is pretty obvious as to what it does, and remove dependent. And this is basically telling the Lisp implementation that for this class, anytime this class changes, go ahead and notify these other things. So it creates essentially kind of a DAG. Well, often you create that. I haven't seen any experiments on what would happen if you say class A depends on class B and class B depends on class A. I'm sure most implementations would look at that and say, what are you doing, and throw up an error. But I can't say that for certain. So be aware that circular dependencies could occur if you are very, very dangerous and ambitious on how to do certain things. Now, if you wanted to access the set of dependents associated with a class, you'd end up using something called map dependence. Map dependence is just nothing more than providing you a list of, if you look at it, you look at the function signature, it will take a particular meta object and look up a function, and you can access a specific piece of information from the dependents. So all this is kind of well and good, but how do dependents actually get notified? Well, dependents actually get notified by having an overrided a method override for the generic function update dependence. Update dependent takes in, if you look at update dependent here, it takes in the meta object, the dependent object that it is looking into, and it will go ahead and notify those guys either, or even in some cases maybe modify those objects depending upon how you've implemented that information. So let's go through an example of this. This kind of is in the end of the introduction for folks who are following along using the metamodular implementation of the Common Lisp MOP spec. We are looking at the dependence maintenance protocol example. So what if we wanted to create a generic so before I get into the example, let me explain something that is actually brought up in the MOP spec regarding portable code in this conflicts. So what I talked about earlier about undefined behavior, this is something that it explicitly stated in the end of the dependence maintenance protocol section, mainly to prevent conflicts between two portable programs or portable programs and an implementation. Portable code must not register meta objects themselves as dependents. Instead, portable programs which need to record a meta object as a dependent should encapsulate that meta object in some other kind of object and record that object as a dependent. So you can't directly register that a meta object is a dependent of another meta object. You need to create another user-defined class to do so. If you don't, the results are undefined, and it depends on which Lisp implementation you are executing on to determine what the behavior results would be and whether or not it would be a good thing or a bad thing. So in general, for folks who are going to use some of this kind of stuff, just don't do it. That's kind of what I tend to see when I see undefined behavior. if you're curious about it, go ahead, write some stuff about it. But in general, for public consumption of code and for production level code, just I'd rather avoid any sort of undefined behavior situations. So the example that is brought up in the spec is something that I think we should take a look at, which is providing this kind of general facility of encapsulating meta objects before recording their dependencies. So what they did specifically is they created something called an updater class. Updater that takes in nothing more than the dependent that you are actually wrapping, and it is a read-only object, so you can't actually go and mess with it. So let's compile that. Then, of course, what we've done here is we have they want to just in the example record to create an at, which is just a function that takes in the record updater takes the class that you are going to add the dependency on, the dependee, and the dependent itself that you're going to be wrapping, and whatever additional initial arguments that you may end up wanting to pass into the class instance itself. What this guy does is, all it does is it instantiates a new function, well, a new instance, which I'm wondering why they actually went in and did this. They just, in the book, they say apply make instance. So we're going to just go and, based on the spec itself, we're going to do apply make instance for the time being. But then we're going to do some cleanup here, because I think some of this can change if we, to make things a little bit clearer, like a direct call to make instance itself. But we'll go through that in a little bit. Once we've created the updater, then this is pretty simple. You call c2mop add dependent. Add dependent will then take the dependee that was passed in. Add it to the updater and return the updater before closing it up. So how can this be used? Well, you can create something called once you have the cache, you can just create something called the flush cache updater, which is nothing more than a class that will flush the dependents themselves in the cache, and then use that to recompute your dependencies and notify them when things have changed. I'll be honest, I haven't actually executed this particular example, so I'm not sure exactly if we're going to be missing something here, but we shall see. Okay. And def method update c2 update dependent. Metaobject is our dependee. We'll just call it Metaobject here for the time being. The dependent, which is our updater or flash. Never seen it written this way, but oh, I got it. Dependent going to be set up to be our flush cache updater. And the rest are arguments. Okay. Then we declare that this is ignored, and do flush cache. Okay, so we don't necessarily need to just do this. Set up. Flush cache doesn't exist, so we could just simply do this. Set up to. Actually, you know what? We'll do this. We'll go ahead and do this. Flush cache dependent updater. Call this dependent object to make it a little bit more straightforward for our example. So what is flush cache? So, sorry, got to compile this guy. No. Is the style warning? Yeah, okay, got it. So, flush cache can be anything that that you want to write. In this case, what I'm going to be doing is instead of creating a simple function, I'm just going to go ahead and create a generic function that has oh, my apologies, I'm being dumb. You have to do this is not needed. Okay. So now, and we're just going to go ahead and just write a stupid implementation of flush cache that is specialized on the updater classes. Or we just pretend that we are flushing the cache. So let's see if we can get this working here. Okay. So let's go ahead and create let's say that we have a class called 2D point. It's kind of the standard one that I tend to go with. And we have this guy has, you know, kind of an x, right? Point arg, point x, and we'll go ahead and say accessor is point x, and a y that is y with an accessor point y. Okay, and let's go ahead and actually, I am doing the wrong thing here. This is on meta classes, not on user-defined classes. Let's go with a different example here. Let's go back to our ordered class. Example. So this guy. Let's go ahead and define an ordered meta class that we defined here. Now, of course, and now let's say that we have this point class here that we are defining. Well, we could also specify here chord updater. Oh, sorry, forgot to compile that too. Okay. Record updated. This guy will take in as our class the ordered class that we just defined. So we do find class ordered class. Our dependee is going to be the point class that we just defined. So we do find class point. Hold on 1 second. This is a generic data. This is actually the wrong ordering. We first do find class updater, which is our actual updater class. There we go. Our dependee is our point class. Our dependent is our ordered class. And then, you know, we have no other arguments. So this should actually generate a new updater class. Now, if you go and look at this guy, our dependent is the ordered class. Internally, ordered class has actually now been it now has a internal connection between itself and the point class. So now, whenever you make a change in your update dependent function, it will then go and if you based on how you implement it, it'll go to all the dependents and update them. Again, this example needs to be a little bit more thorough than the one that's in the book. When I read this, I thought that this is the ordering that I had was correct, but it looks like it's wrong. So it was wrong. So I need to go through that a little bit. I'll provide an update to that particular example later on. So let's move on to chapter 6. This is kind of the final thing of the spec. This is actually your API reference in the book. Now, folks who are reading the Metamodular site, what they were kind enough, the authors of the Metaobject protocol were kind enough of doing is they actually went ahead and split the accessors of the class, generic function, method, slot definitions into the APIs associated with initialization and the APIs associated with actually querying the methods the meta objects themselves. On top of that, there were a couple of additional other methods and generic functions that they've defined, like and documented, like ensure class using class, and so forth. I don't think there's much. That's when I read this, I didn't see that there was much covered in this chapter that wasn't covered in chapter 5. Chapter 5 actually did a pretty exhaustive coverage of the different protocols that are around them. Now, granted, they didn't go to every single API in detail. For that, I think we would have to come up with some more and better examples than were presented in the book. That's fine. We're planning on giving an overview of some examples in the book. In GitHub repositories, and try and go through them. But that's it, actually, that I was going to cover today. I wanted to mention to folks who have the book in themselves that in Appendix D, there is a full-fledged implementation of the Metaobject protocol for Closette. I've slowly been going through it, particularly because of the fact that there was I had to map some of the things to how I think Common Lisp kind of like evolved because of, for example, for folks who are looking at this, there's a section on how they're exporting symbols that doesn't quite match with package exports, and I was like, well, how would this look like if we're writing this now through the standard Common Lisp? So I started going through that a bit just so that for my own education. And then the other thing that was kind of mentioned is there's in Appendix E, there's also a nice cross-reference to methods that are in the Closette implementation. I didn't realize that existed. But that's it for today. Are there questions? I know today's kind of a short episode. I wanted to at least cover the last stuff of the protocols themselves. Starting next week, and then before we go on our break for the game programming series from the Metaobject case studies, I was hoping to cover an example, a through and through example that one might use, and then we could start looking at libraries that leverage the Metaobject protocol itself. But I'm opening the floor for questions, comments, discussions. So those folks that are on YouTube, let me know what questions you have. Michael Gargano, do you have any thoughts or comments that you might want to bring up
No, not really.
Yeah, this is a pretty thorough piece. Like I was quite surprised just how many different things that they come up with. So I've been kind of going through the exercises now to see, what how I might end up leveraging some of these things to implement some of the features of other languages, like the anonymous inner classes things that JS brought up last week, and as well as I was looking at uh, completing that encapsulated class example that I was going through. All right. Okay. So tune in next week. Um, Again, we will be hopefully covering. Definitely, we're going to be covering an example that is using the Metaobject protocol. Might be a contrived one that I brought up. Might be one of the GitHub repositories. Let me know your thoughts. I'm available on Mattermost almost all the time. Just ping me. I usually try to respond as quickly as possible. And if there's a particular project that you want to like go through and understand, let me know, and we'll try and cover it. But if that's it, I'll see you guys next week. And thanks for joining us.
Thanks.
Thanks.